status register. This is something new for those who are actually coming from O-level, because the status register is not part of the syllabus in O-level. This status register is also under control of the ALU. This status register is also under control of ALU. Now what this status register does, it is also a general purpose register which is used for so many things. So it has got that thing that every bit of it is having a different purpose. Like in accumulator, you can place data. If you place the data, the whole accumulator is occupied. But in a status register, the different bits are used for different things. Like, let me tell you, if you do remember the additions, binary additions, there were carries and there were drops. So if there is a carry, one bit of the status register will be set. Means it would have one that, yes, there is a carry. Similarly, if there would be a drop, another bit which is responsible for drop will be set. Otherwise, it will be reset. So it contains bits which can be set or clear depending on the operation. For example, overflow, the drop is overflow in the calculation and the carry. There might be occasion when your program would have an error. That error would not let your program go any further. That is called execution error, program runtime error, or whatever. Those errors, if they occur, there is a bit in the status register that will be set as well. So that this status register is also under control of, like accumulator, of ALU. So this is status register. All right. There is another register called index register. This index register is used when carrying out index addressing operations. Addressing operations are what? Index addressing operations are when we want to access consecutive memory locations. Let's say I want to add data from 56 to 66, 11 memory locations consecutively. So I would be requiring a loop, as you would know loops. So in assembly language, for, next, and while are not there. So what we do, we use rather index addressing. Right, so that addressing is used. So index register are also under control of control unit. All right, like any other register. So index registers are in control of control unit as well. We will discuss the working of index register exclusively later, but not now. Okay, now, so we have got index register, status register, CIR, and then we have got system clock. System clock. This is another new thing. The system clock is responsible for the speed of the microprocessor. System clock. All right. So this system clock is actually giving signals to control unit and arithmetic and logic unit. So what does the system clock does? System clock is used to produce timing signals on the control bus to ensure this vital synchronization to take place. Without the clock, the computer would simply crash. Now, what is actually a system clock? You might have heard of the speed of the microprocessor, 2 gigahertz. Giga means billion, hertz means billion cycles, means 2 billion instructions per second our processor can carry out, can execute. Let's say, this is just analogy. Later we would have a different version of it. So when this clock ticks, the next instruction starts getting executed. Faster the clock, faster the execution. You get it? As soon as this system clock ticks, the control unit starts next fetch, decode, execute cycle. You get that? As soon as the system clock ticks, ALU does next operation. So faster the clock, faster the computer. Slower the clock, slower the computer. Have you ever heard of this term, overclocking? Means that the company has set the microprocessor a bit under power. Under power means that it can perform more, but it is actually not performing to that level. So we can always go to BIOS setting and we can give it a boost by setting the speed to bit more than what is set by the company. And that is called what? Overclocking. But that overclocking's consequence is heat. So when computer works fast, there is heat generated. Anyway, so I hope that you got the idea of this. So this whole thing is called microprocessor. What do we call it? Microprocessor. We call it what? Microprocessor. So this is our microprocessor. Let's make it in a different color so that you have an idea. So this is whole microprocessor. Okay, so what microprocessor has got? Microprocessor has got system clock, ALU, index register, status register, accumulator, control unit, PC, CIR, MAR, MDR, oh, a lot of it. Okay, and this particular memory RAM is also called the part of microprocessor, but I told you that it is residing outside. So the main components of the processor are arithmetic logic unit, the control unit, the system clock, and the immediate access store. Now this is something new, immediate access store. IAS, immediate access store. Immediate access store. IAS. So now immediate access store holds all the data and programs that the processor needs to access. Now you can understand that what this immediate access store is actually. So it holds all the data and the programs that the processor needs to access. The CPU takes the data and programs held in the backing store and puts them into the immediate store temporarily. What is backing store? Backing store is a storage, hard disk, DVD. This is done because read and write operations carried out using the IAS are considerably faster than read and write operations over the hard disk or the backing store. Consequently, any key data needed by an application will be stored temporarily in IAS to speed up the operation. The IAS is another name for the primary memory, which is actually what? RAM. Alright? So IAS is actually what? RAM. Random access memory. This is your RAM. Mind it. Immediate access store. The IAS holds all the data and programs that the processor needs to access. So you might have this question coming up. What is in the RAM? So you would say all the programs and their data which is being executed at the time. Alright, so they all are actually there. Okay, so this is the constitution of the microprocessor. So do you know that how much have you studied? You have studied a lot. You have studied the formation of microprocessor. You have studied registers, special purpose and general purpose registers. General purpose, remember, status register is also a general purpose register. You have studied what is system clock, what is control unit, what is ALU, what is fetch, decode, execute, cycle, what RAM does. This is all the information that we need to understand the von Neumann model and the system buses. Don't forget that. So let's take everyone one by one. Let's start with the what do we call it? The fetch, decode, execute. Architecture definition. Hold on. Now see, von Neumann architecture, if they say state, define, describe, what is, whatever, or they say von Neumann architecture, computer architecture, just the architecture or idea of a stored program. In any of the cases, you have to tell them these four things. A basic computer architecture as described by the mathematician John von Neumann, also known as idea of a stored program. It describes a single processor composed of control unit, arithmetic logic unit, and memory unit. Yes, these were not there before him. Both programs, means instructions and the data, are in binary form and thus can be stored in the same memory. They are indistinguishable in the binary form, but still they can be kept in the memory. How they act upon it, we will discuss about it, but the short idea is that if you look at this picture, what do you see? If you see this LDD56 thing, Do you see that LDD56 thing over here? This, it is one instruction, LDD load directly from address 56. And these instruction and address are at different memory locations. This instruction itself is at 50 and this data is at 56. That means that this instruction now knows that where the data lies. No matter if this instruction is in the binary form or whatever the form, this instruction itself knows that where the data lies. So data lies at what? Location 56. So instructions themselves know that where the data is. So as programmer, we don't have to be worried about it. As programmers, we don't have to be worried about it where the data lies. Instruction knows itself. Alright? So even if they are indistinguishable, means they both are in binary and they cannot be seen and understood. If they are in binary form, doesn't matter. The instruction knows that where the data lies, so the instruction would access the data by itself. Alright? So now, a single processor composed of control unit, arithmetic logic unit, and memory unit. Second is both programs or instruction and data are in binary form and can be kept in the same memory location, and they are indistinguishable in binary form. It uses input, output, and storage devices to acquire and store data in programs. So this should be data in programs. Beforehand there was no storage. If there was no storage, means no stored program. If no stored program, you cannot program. If you cannot program, you cannot make general purpose computers. Means the whole progress that is now that we have as far as the computers are concerned would not be there if he or Alan Turing would not have thought of it. It's a sequential machine. I told you that PC increases itself by 1. For that nature, it is a sequential machine because it executes one instruction, then the next, then the next, then the next, and it goes on and on and on. Unless you deliberately change the instruction address. But if you change instruction address to another address in the PC, from that address onward it would go sequentially. So this is a sequential machine. That is, it executes instruction one after the other and in the written sequence. And then we have got what von Neumann architecture's fetch, decode, and execute cycle. This is what we have discussed. Von Neumann architecture, fetch, decode, execute cycle. From PC, the address goes to MAR. When I say goes to, it means that it is copied. Content from PC is copied to MAR. Then MAR with address bus points to the RAM. Data from the memory address mentioned in MAR arrives in MDR. And that bus when points to the address from that address, content arrives in MDR and through the data bus. And in this case, the content is the instruction itself. Data from memory address mentioned in MAR arrives in MDR. From MDR, instruction is then copied to CIR. This is called what? Fetch. If the instruction has got address part in it, like I just have discussed, LDD56. So 56 is what? Address part. Address part means that now the system requires the data from the 56 so that it could be loaded to accumulator so that it could be useful. LDD56 means load directly from the address 56. We will discuss these instructions later. That is next lecture. So if the instruction that has arrived in CIR has got address part in it, if you would have noticed that there are two types of instructions that I showed, one that has got address in it, like these three, and one that has got no address in it. So there's no address in here, there's no address in here. So if the instruction has an address part in it, if the instruction in CIR has the address part in it, then it is copied to MAR so that the data from that address could be fetched. And the last one is instruction in CIR is then decoded and executed. As I said that you would not have to learn actually how the decodation or execution happens. All you have to do is to learn that CIR does it. So these two instructions are part of decode and execute. If the instruction is without address, it is simply decoded and executed. If it has got address, then that address will be placed in MAR so that the data from that address could be fetched and worked upon. So this is called fetch, decode, execute cycle. They will ask you to write about it. So now the fetch, decode, execute cycle has got another form, which is called register transfer notation. This is same. This is sort of mathematical form of this fetch, decode, execute cycle. RTN, register transfer notation, is symbolic notation used to describe the micro operations between the registers. When the data is moving from register to register, these are called micro operations. So these micro operations, when they are described in symbolic form, like in mathematics, it is said to be register transfer notation. And I told you that it is actually another form of what? Fetch, decode, execute cycle. The term register transfer means the availability of hardware logic circuits that can perform stated micro operations to the same or another register. Like PC moves to MAR, MAR moves to memory, memory moves to MDR, MDR moves to CIR, and CIR is execution with the help of ALU and accumulator. So if they are connected and they are actually holding up each other for the work, and then they are handing the data and all that, that is all actually micro operations. So following is the register transfer notation to denote the micro operation performed during fetch, decode, execute cycle. Register transfer notation is something big for your syllabus. It is just confined to fetch, decode, and execute cycle. So these two large brackets means the value, the content. So if there is a variable a is 5, so this means we are referring to 5. This thing means we are referring to 5. Mind it, okay? But if I write like this, so it means that I am generally referring to a. But if it is in the bracket, it means that I am referring to the value of a. They might look like the same, but in computer these are two different things. Okay, so what does it mean? The content of PC. See, how the content has reached to the program counter is not our concern. This is not in our syllabus. So it is understood that whenever we discuss Fedgy code execute cycle, we will start from what? PC. Alright, so we will start from PC and we will consider only what happens afterwards, not before that. So the content of PC is transferred to MAR. Alright, and the content of PC is incremented by 1 and assigned back to PC. So we can say that the PC has incremented itself by 1. So let's say if it was 50 plus 1 becomes 51 and it is assigned back to PC. So the content of PC is increased by 1. Now these are two brackets. Inside bracket, let's say MAR has got address 56. So when I say MAR and at address 56 in memory, let's say at address 56 in memory, let's say I have 100. Okay. So when I say MAR, I mean 56. When I say the content of MAR, I mean 56. But when I say the content at the address mentioned in MAR, then I mean 100. So inner bracket means the content of MAR, that is 56. Now 56 is taken. So at first stage, it will be taken like this, which is 56. At second stage, it will be taken like this. Whatever is at 56, that is 100. Mind it. So this is under wala bracket and this is bahar wala bracket. Get the idea? So the content of MAR is actually the address in the memory. The content of that memory address is then fetched and placed in what? MDR. In this case, it is an instruction. So content of MAR is memory address, and from that memory address, from memory, the content is fetched and placed in MDR. Means simply the instruction from memory, it has arrived in MDR. And the content of MDR, which is an instruction, goes to then CIR, and over here, the bracket means that CIR decodes and executes it. That's it. So you would have to actually remember this in this shape. They might give you this as to write as a whole, or maybe in the form of blanks, or maybe they shuffle it and ask you to put it in order. Whatever, you need to remember all these 5 things. These are no different than Fedgy code execute cycle, and register transfer notation is only limited to Fedgy code execute cycle in your syllabus. So the content of PC goes to MAR, PC increment itself by 1, the content at the MAR is the memory address, from that memory address content arrives in MDR, and from MDR the content arrives in CIR, and CIR decodes and executes it. Get the idea with it? Now, this is what you have learned, and now definitions. Arithmetic and logic unit, a part of microprocessor. It is an independent unit that takes its data from memory registers and hold accumulator register. It does all the operations and it works in sync with system's clock. Faster the clock, faster the work of arithmetic unit. ALU contains the logic circuit to perform mathematical operations like additions, logic operations like AND or OR, and logic bitwise operations. Bitwise operations are those which we have done in additions, column by column by column. That is bit by bit by bit. ALU is supposed to be the head of microprocessor that does all the operations that it requires. Then we have got control unit. I'll be sharing these slides with you today. Do not worry. Control unit is a component of the CPU that directs the operations of the processor. It tells the computer's memory, ALU, and IO devices how to respond to instructions that have been sent to the processor. It is all of the steps performed during Fedgy code and execute cycle are coordinated or synchronized and completed by the register under the control of control unit. So without control unit, nothing could happen. All input, output, and everything. Fedgy code execute cycle, it is all happens using control unit. So system clock. A clock inside the computer that is responsible for the synchronization of all the internal components, that means they all do their work, and when the clock is high only. High only means that you see system clock goes like this, on, off, 1 second, and then let's say if it is 1 second cycle, 1 second has got so many milliseconds, so many microseconds. So clock does not go by second. So clock goes like on, off, on, off, on, off, on, off, on, off. So when the clock is on, only then system works. When it is off, it does not. So that off time is actually the time when the thing is happening. On time is when the system clock is saying that go on for the next thing. ठीक है, मैं आपको बोलूँ कि जल्दी जल्दी काम करो, चलो अगले पेज पे आ जाओ, आपने जितना काम कर लिया वो आप कर लेंगे, फिर आप अगले पेज पे आ जाएंगे, फिर मैं आपको थोड़ा सा टाइम दूंगा, फिर बोलूँगा अगले पेज पे आ जाओ, ठीक है? So अगली इंस्ट्रक्शन पे आ जाओ, ये बोलता होगा system clock. So when the clock is giving time, it is off. When the time for the next instruction execution starts, it is on. So system works only when the clock is on. And then we have got instruction cycles. Instruction cycle and clock cycle are two different things. As I said that I just described one of the instructions, which was LDD56, means that load the data directly from the address 56. And then I said that in the execution part of the Fedgy code execute cycle, that address 56 needs to be placed in MAR so that the data from that 56 address could be fetched and could be used by the microprocessor for the execution of this current instruction, which is LDD56. जैसा कि मैं आपसे बोलूँ कि what is at page 9, so you would go to page 9 and then you will fetch what is at page 9 and then you will tell me. But the instruction is go to page 9 and fetch it. So you would have to go to page 9 to fetch it. So instruction cycle, it is a time period during which one instruction fetched from the memory and executes when the computer is given an instruction in machine language. So the whole instruction which is being executed is instruction cycle. And clock cycle, the clock cycle is the time to adjacent pulses. Adjacent means on and off together, generated that set up the tempo of the computer processor. On off, on off, on off, on off. When it is off, the program is actually doing something. When it is on, next instruction. It is generally understood that the faster the clock cycle, along with other factors like bus width and the reasons for the better throughput of the computer, as only clock speed with other bottlenecks can be the reason for the faster microprocessor. What does it mean? What if microprocessor's clock, the system clock is faster, but the instruction requires, let's say, 3 or 4 things to do before moving on to next instruction? So 3 clock cycles will be used. If the instruction is requiring just 1 step to complete, then 1 clock cycle is required. If the instruction requires 2 steps to complete, then 2 clock cycles are required. So it means that faster clock is better, but it does not mean that in every single clock cycle there would be just 1 instruction cycle. Instruction cycle might be having 3 steps, so those 3 steps means 3 clock cycles. Instruction might be simple, instruction might be maybe complex. So if instruction is simple, it might go away in just 1 clock cycle. If the instruction is complex, it might go away in like 5 clock cycles. So faster the clock, better, but clock speed is not actually the measure for the faster speed of the program. In terms of time, it might be. In terms of number of execution, it does not. Alright, so let's say we have got 4 instructions and all 4 instructions are simple instructions. So if they are simple instructions, it means that 4 clock cycles are good enough. So 1 instruction cycle is now equal to 1 clock cycle. But if these 4 instructions, out of these 4 instructions, let's say instruction number 3 is actually complex and it requires 5 clock cycles. So it does not mean that now the whole program will be executed in 4 clock cycles. It will require 1 clock cycle, 2 clock cycles, 6 clock cycles, and 7 clock cycles now. Alright, so clock cycle is not a measure for how long the program will take to get executed. It might be a measure for the faster computer. Alright, it's like a person can really run fast. Alright, but what if you ask him to run uphill? Obviously the time, he would run fast, but the time will be increased now. Alright, it does not mean that he has become old or he has no energy. Yes, he has energy, but now the task is complex. Get the idea? So his energy, his fastness, his rapidness is actually shown to us as best when it is in simple conditions, and it is shown to us as worse when it is complex situations. Alright, so instruction cycle is the cycle which is for 1 instruction, the time that is required for 1 instruction, and the clock cycle is actually, clock cycle has no difference, it is always the same. But remember, instruction cycle, it only starts when the clock says so. So clock cycle is mainly used to start something and to go on with it. But instruction cycle is actually the instructions time that it will take. The instruction time that it will take will be counted in clock cycles. Alright, so 1 instruction might take 1 clock cycle, 1 instruction might take 4 clock cycles, 1 instruction might take 3 clock cycles. Alright, so IAS was the new thing. So RAM is actually, so whatever that is being executed and its related program, whatever is being executed and its related data is actually held up in immediate store. Immediate access store is where the computer has to have everything so that it could take notice of it and use it. When computer requires anything, it looks into immediate access store. When it does it, when it completes it, and it puts it back in immediate access store. And immediate access store is nothing but what? The RAM. Now, registers. Accumulator. I told you that it is general purpose register that holds the data produced during the execution of the program, the data that is arrived in microprocessor and yet to be utilized by the microprocessor, data, not the instruction. Data which will be stored back in the RAM and waiting because the address bus is busy. And if it, now there is one important thing that I need to talk about. If MDR, memory data register, has got instruction in it, then that instruction would go to CIR. But what if it gets data in it? Then that data will be transferred to accumulator. And then through control unit, that accumulator will utilize that data. That control unit will utilize that data in accumulator. But data doesn't go to CIR. CIR only have what? Instruction. So if instruction arrives in MDR, it goes to CIR. If data arrives in MDR, it goes to accumulator. Mind it. Alright. Program counter. Responsible for the sequential execution of the program. This register holds the address of the next instruction. This is very important. So store the address of the next instruction to be read. Alright, from the memory. Memory address register responsible for holding the address of the data or instruction to be fetched and written back to the memory. The instruction of data that has just arrived or going out will be first placed in memory data register. Mind it, memory data register is like the gateway of the microprocessor. Whatever comes in and goes out, it first stays in that gateway. That is the gate. All right, MDR. It is also called what? MDR. I told you that. All right. Current instruction register. It executes and decodes. Decodes and executes. All of the registers listed here, apart from the status and index register, are used in fetch, decode, execute cycle. Okay. Index register and status register are not used in fetch, decode, execute cycle. We will discuss about index registers later when we will be studying memory addressing techniques. A status register. Let's see if I have, yes. Index register, mostly written as IX, and sometimes you might see it with IR, but in your syllabus it is IX. A value in this register is used as offset. Now, what is offset? Offset is actually displacement. Let's say if the address is 5 and displacement is 6, so 5 plus 6, 11. So this index register makes the address go ahead from the address which is base address. We will discuss about it. So let's just discuss at the time. Let's just discuss status register. And we will discuss about index register and base registers later when we will be studying memory addressing techniques. So status register is used when an instruction requires some form of arithmetic or logic processing. Each bit in this register is known as flag. So one of the bit in this register, this is a general purpose register and used to hold many different types of status during the execution of program. So that execution of the program is either the arithmetic or logic, because this is being used by arithmetic logic unit. I told you about it. Each bit of it is known as what? Flags. So flags are set and clear, set and reset, set and clear. Putting 1 is set, clear or reset is 0. So it has got carry. Carry is set to 1 if there is a carry following the addition operation that we have done. If it has got a negative flag, N. Carry C, N means the result of the operation is negative now in 2's complement. It has overflow, V. Overflow is called what? V. Alright. So bit overflow is called V. Carry is C. This is the name of that particular bit. Then negative. I have not mentioned it over here, but we have got negative as well. Alright, and then we have got 0 flag. It is set to 1 if the result of an arithmetic operation is 0. So we have got 0 flag Z as well. Which is Z, if the result of the operation is. And then we have got program error or comparison. Error is E. There are different names of these bits, but think of it like a byte which is having different bits. Every bit is having a different operations representation, and this is called status register. Alright. So we have got parity flag as well, and there are so many others. So just leave it out. So status register, as far as this, the definition is concerned, this is a general purpose register used to hold memory, used to hold many different types of status during the execution of program, and that execution is actually nothing but what? Just the logic and arithmetic operations. And then the last thing that we have discussed today was buses. So one Neumann architecture system buses. So control bus, this bus is a bidirectional. Data can come in and goes out. So control unit use it to sync with all the parts of the microprocessor and outside. So this bus is a bidirectional bus and helps system to coordinate between microprocessor, control unit, and other parts of the system like main memory. This bus is responsible for carrying interrupt signals. We will study about it. Interrupt is part of one Neumann architecture's topic over here in your syllabus, and device status. Alright, and address bus. This is a unidirectional. I explained a lot about it. This unidirectional bus is responsible for carrying address to the devices for either storing data at those addresses or fetching data from those addresses. And then we have got data bus. This bus is used to carry data back and forth between the microprocessor and the other parts like RAM IAS. So this is it today. Thank you for being with me for that long.